With that background, it's finally time to dive into the feed-forward network. So, just as in our example, we're going to have a hidden layer and an output layer. Remember that with a neural network, a neuron is synonymous with a weight vector, right? So, whenever I say neuron, just think weight vector. Both the result of our hidden layer and our output layer will maintain three rows. Because remember, the purpose of feed-forward network is to abstract more complex features of each independent token. So now that we know how beam, me, and up are attentive to each other, we give the model the opportunity to create, for the lack of a better word, more complex, rich features out of the features we've provided. And again, by features, I just mean the dimensions, the embeddings. The number of neurons at our hidden layer, though, is going to be 4 times the number of dimensions our model has. What we'll see is that this will actually make the representation of each of our tokens after the hidden layer 4 times longer. Then the neuron count in our output layer will be the number of dimensions again, contracting the output back to our original dimension count. This expansion, nonlinear activation, and then contraction of our features, of our dimensions, is what creates the space for the model to deduce deeper context from its original features, and what results in what one might call the knowledge that the model has, or the illusion of knowledge. So let's clean this up and get started. Since we have 8 dimensions, we will have 32 neurons in our hidden layer. The shape of our neuron is size d by 1. So we'll have d rows and 1 column per neuron. In this example, since we have 8 dimensions, we'll have an 8 by 1 weight vector. What we have to do is we have to run each of our 3 tokens through each of these weight vectors. So let's zoom in on our first example. Since the structure of each of our tokens has the shape 1 by 8, 1 row and 8 columns, or 8 dimensions, we can compute the dot product of each token with each weight vector. The dot product of our beam embedding with our first weight vector is a scalar, since it's the dot product of a vector and a vector. The resulting output then is ran through our activation function. While GALU is the more common activation function for transformers, it's much easier to do a quick example with ReLU just because of how simple the math is. So let's pretend the resulting scalar value of beam is 5. Remember that with ReLU, if x is greater than 0, return x, else, meaning if it's 0 or less than 0, return 0. This results in our graph looking like this. So when we put 5 through the ReLU function, the output is 5. Now we do the dot product of me and our weight vector. The answer is -2. And when we put -2 through our ReLU function, the output you get is 0. Finally, the dot product of up with the weight vector. Let's assume the output is 0.5. And the output of the ReLU function is 0.5. We have officially introduced nonlinearity into our equation, because while the weight vector affected all of our tokens the same, the ReLU function didn't, because it left a few of the values the same and some not. While one way to view this is as 3 independent vector dot vectors resulting in 3 independent scalars, a cleaner way to view it is as we have earlier in this video, as the dot product between a matrix and a vector, resulting in a vector with 3 scalar indices. Now that we know the math of a single neuron, we can just extrapolate this math out for each respective neuron, which is what we'll do now. Now we have our input matrix, which gets dotted with each weight vector, resulting in an output vector of 3 scalar values each, respectively. I'm sure you're 2 steps ahead of me, but as we can tell, this is actually a matrix dot a matrix, resulting in a matrix, where each column output is the result of a different weight vector. So let's zoom out real quick. I had 2 real reasons why I wanted to show it to you broken out like this initially. First, because I want to make it clear that the activation function happens at each independent scalar output. And second, because whenever neural networks are talked about, people always bring up the concept of neurons. And when people reference neurons without a visual like this, neurons seem a lot more abstract and confusing. People often compare neural networks to how the brain works, which isn't not true, but when you start talking about brains and you start talking about neurons, There's a degree to which that overcomplicates what's actually happening when a neuron really is just the dot product plus a nonlinear transformation. Okay, now we can visualize these as matrices, right? So we have our input matrix, which is size 3 by 8. We have our hidden weight matrix, which is of size 8 by 32. This successfully extends our embedding representation of our tokens to size 3 by 32. Our output layer then, to ensure we bring it back down to 8 dimensions, is of size 32 by 8. We compute this dot product of 3 by 32 dot 32 by 8, resulting in our original shape again of 3 by 8. This feed-forward network has a total of 32 neurons in the hidden layer and 8 neurons in the output layer. Now, let's zoom out a little further. All we have to do now is similar to the attention layer. We have to apply the residual connection. We do this for the same reason as we did earlier, to provide some level of stability to the model as we get deeper and deeper. We then normalize, which, like before, brings the mean of each token back to 0. And that completes the encoder. Now, because the attention layer takes in a 3 by 8 and outputs a 3 by 8, the feed-forward network takes in a 3 by 8 and outputs a 3 by 8, we can stack as many encoders as we would like to add depth to the model. Just as an example, the original Google BERT model, which was an encoder-only model, had 2 variants. BERT Base, which had a total of 12 encoders, and BERT Large, which had a total of 24 stacked encoders.